looks like we're all here. All I can say is it's some kind of sadistic thing of Emmanuel's that he is making you listen to 2 lectures from me in the morning and a lab all afternoon. So blame it on him. I did not campaign for this, put it that way. Okay, so I'm going to have another little lecture here now that leads into hydrolyte and you guys actually using it to do real science. And that's talking about the whole closure business. And there's also some stuff at the end about how to design the perfect field experiment, but I'm not really going to go into that. I just kind of threw it in there for reference because I'm going to be tired of talking by the time we get through the first part. So what I'm going to do is just show you several examples of how people have done advanced simulations with hydrolyte and show what is necessary to get agreement between hydrolyte output and things you measure. So that's the whole closure business. And so as you sort of learn now, you have to supply the IOPs and boundary information to hydrolyte, and hydrolyte doesn't know anything about your water. So we'll see a little bit more this afternoon on how to read your own data files in. So you've measured, absorption and scattering with an ACS. So you've measured, bottom reflectances. You've measured chlorophyll profiles. How are you going to actually put those into hydrolyte? And so we'll talk about that in the lab this afternoon. And then if you just think about, I want to do a hydrolyte run and get closure with the things I measured. So what all do I actually need? Well, you've seen now hydrolyte inputs. You need to know the absorption coefficient as a function of depth and wavelength. So maybe you got that from an AC9, maybe a spectrophotometer. You need to know the scattering coefficient. So maybe you got that from your AC9 or an ACS. You need to know the phase function. So that's almost never measured, but maybe you have a backscatter instrument so you can measure the backscatter coefficient, and then you have the total scattering coefficient from up here, and then and you would get the BB from something like a Hydroscat, a BB9, one of those instruments. And then you could use the ratio and let hydrolyte generate a Fourier-Ferrand phase function that has that backscatter fraction, which in general is going to be a function of depth and wavelength. And then you have boundary conditions. So how rough is the sea surface? Well, that's parameterized by the wind speed. There's other things that you do know, sun location. And you probably don't have a sky radiance distribution, but hydrolyte can model that, and you may have shallow water with some bottom reflectance, and maybe you have measurements of the bottom reflectance, so you can put that into hydrolyte. Then its outputs, of course, are the radiometric variables, and what you can usually measure to compare with hydrolyte are things like LU and ED as functions of depth and wavelength. So that's kind of the minimum thing you would measure if you went to the field. You can compare hydrolytes, AOPs like KD and remote sensing reflectance with whatever you measured in the field. And the most common thing, of course, is remote sensing reflectance. So you measured ED and LU and some way turned those into RRS. So then here's an example of about as close as you're ever going to come to doing this. There was an ONR funded experiment called HYCODE, stands for Hyperspectral Coastal Ocean Dynamics Experiment. And the stated reason or purpose of this program was to understand water leaving radiance, all the things that affect it. And so here's some data taken off the coast of New Jersey, location, it was kind of a cloudy sky, wind speed. And so here's what we had. We had absorption in C from an unfiltered AC9 at those wavelengths. We had dissolved absorption from a filtered AC9. We had backscatter from a Hydra Scat 6 at those 5 wavelengths. We had the VSF at 100, and that actually uses the VSF at 140 degrees. We had backscatter derived from VSF measurements at 100, 125, and 150 at 1 wavelength from an Eco VSF. We had an instrument built by the Ukrainians called the volume scattering meter that actually measures the volume scattering function from 0.6 to 179.6 degrees at 530 nanometers. And then we had ED and LU and the Sky ED, and then we had values from instruments there. Then we had hyperspectral values of ED and LU from a TSRB at 123 wavelengths. And most of these instruments have somewhere around the 10 nanometer bandwidth. So there's what we had to play with, both inputs to Hydra Light and things we could compare with its outputs. So see how well we did then. Here's plots of the IOPs. So here's absorption, particulate plus CDOM. Here's just the CDOM part. The water here was about 17 meters deep, so that's the end of the profiles. And then here's the particle part. So you notice the total absorption, it's pretty uniform for the first 6 or 7 meters, and then the values drop down. So here is the particle part, and then here's the scattering by particles, maximum up here, comes down. You see a little bump there, but when you look at the backscattering by particles, it's kind of uniform, and then there's a big bump at the bottom. And the theory here is that this is resuspended sediment, but we can't actually prove that because people didn't take water samples down there. But since the bottom's 17 meters deep, there's pretty good currents. This is probably small resuspended sediment particles in the bottom 3 or 4 meters that are making a big bump in the backscatter, but a little less noticeable bump in the total scattering. And then here's just a plot of beam attenuation and chlorophyll. So a lot of chlorophyll at the surface, not much chlorophyll at the bottom. No little bump in chlorophyll that would explain this. So that's why we figured that's probably sediment. It doesn't show up in the chlorophyll. And of course, chlorophyll, the shape of this curve is corresponding pretty closely with beam C and the particulate absorption here. And of course you can see a little bit of a bump here in beam C corresponding to that. Okay, so anyway, there's the IOPs we had, wavelengths from 412 out to 700 roughly. Okay, here's the volume scattering data we had at 530. So this is at 2 meters depth. So the blue curve is this actual measured value from the volume scattering meter. The red dot is the corresponding Fourier-Farrand phase function, and the green curve is the Petzold function. So you see Fourier-Farrand is really close. Here's the same thing plotted on a log linear axis. And you see Petzold is much higher in backscatter fraction than the measured or the corresponding Fourier-Farrand. And the rise here is probably at least partially real, and then there's some funky little bumps here that are probably some kind of instrument artifact. Okay, here's another sort of plot of this. Here's the backscatter fraction, okay, at 442 up through 683, and then the chlorophyll. And you can see at the surface where it's high chlorophyll, so a lot of phytoplankton, which tend to have a low backscatter fraction, you can see the backscatter fraction is around 0.5%. As you go down, the backscatter fraction increases to, depending on the wavelength, between 1% and about 1.5%. And so that's kind of consistent with the bottom water having a lot of high index of refraction minerals in it, and they're smaller particles. They have high backscatter fraction. Here's the backscatter fraction of the Petzold phase function. It's 1.8%. It's higher than anything here. So if you just came along and said, I don't have any data on backscatter fractions or volume scattering functions, I'll just use Petzold, you're going to be way too high here by, like a factor of 3 to a factor of 30%, depending on the depth and the wavelength. So then here's another plot of the backscatter fraction where it's partitioned from depths less than 6 meters and greater than 14. And this is now the wavelength plot. So you see for the depths up here, there's a little bit of wavelength dependence, but basically it's about 0.04 or 004 to 005. But down at the bottom for 14 meters downward in this area, there's a stronger wavelength dependence here. Not huge, but it's certainly quite noticeable. And then these are all the depths in between. So that's just kind of, the first thing you do is plot out all your data every way you can and look at it and see if something looks funny and see what you can figure out. Okay, so now we start running all this data through Hydrolite and see what comes out. Okay, so here's EDs at the different wavelengths, 443 up through 683. So if you just look at the first one here, okay, when I do a Hydrolite run and I assume a Petzold phase function, which we know has too much backscatter, or too much backscatter fraction, I get the green curve. Now when I use the measured volume scattering phase function, that's the blue curve, and the Fournier-Ferrand is the red dots under there. They're basically identical. The black curve is the actual measured ED, and up here they're in good agreement, and then it gets so dark the instrument can't measure it, so you start getting this roll off, which is simply instrument effect. If we look at 489 or 533, for example, now there's plenty of light for the instrument to measure ED all the way to the bottom, and you see there's basically what I would humbly call just about perfect agreement between the measured ED, the ED from the measured phase function, and the ED from the Fournier-Ferrand phase function, and then the Petzold doesn't have enough ED, and that's just almost an order of magnitude by the time you get to 14 or 15 meters. So then, same story, other wavelengths, they may be a little off here, but basically they're pretty good. And Petzold is always off here by having too much or too little light. Now, does that make sense? Yeah, Petzold has too much backscatter, or backscatter fraction, relative to the others. So the light's propagating down, and Petzold is backscattering a lot of that back upward. So the light's being backscattered upward, so it doesn't make it down to here, so that's why ED is too small. Now, we go to LU. Here we are here. Okay, so once again, the black is measured. LU's not as much light there to play with as there is with ED, so the instruments roll off at a little shallower depth. But up here, the measured VSF and Fournier-Ferrand are doing pretty good until the instrument begins to lose it. And then Petzold has too much LU near the surface. Well, does that make sense? Yeah, that's the light that was backscattered out of ED and is making LU too big. So you look at this and say, okay, cool, it all makes sense. I understand what's going on. The Petzold phase function was simply giving me too much backscatter, which made ED too small and LU too big. And the measured and the Fournier-Ferrand phase functions are doing a pretty good job of agreeing with the measurements. So life is good. Stop at this point, publish the paper. Here's the ratio of LU over ED at a 0.5 meter depth made by several different instruments and then simulations. So the black curve here is a Hyper TSRB Satlantic instrument. The purple dots are from their ocean color profiler. The green is simulated in Hydrolite with Petzold, and then the red simulated in Hydrolite with Fournier-Ferrand, and the blue is simulated in Hydrolite using the measured phase function. So once again, Petzold, too much backscatter, way too high by a factor of, as much as 2 here. There's, in theory, the black line and the purple dots would be identical, but you have differences because they're different instruments and all of that. And you see it's probably just coincidental, but at least it's reassuring that when I use the measured volume scattering function, I'm right on the money here with the purple dots. The Fournier-Ferrand is pretty close, but it's a little bit lower. So that's just the way it turned out. And the moral of the story is you get way better results by using a measured volume scattering function than just pulling the wrong one out of the air. Okay, here's different experiments now. This is a California experiment. Heidi Dears, I think, will be here next week to give us a lecture on stuff. And she's as good as you can get for going out and measuring these kind of measurements. So she has 3 instruments, a HyperPro, an analytical spectral devices, and a Hyper-TSRB. So the blue line, the purple line, and the yellow line are all measurements. In principle, would all be the same, but you can see what kind of differences you get from one instrument to the next. And then she did do 2 Hydrolite runs, kind of guessing phase functions because she didn't have that information. And so the teal color here is one Hydrolite run, and this one is the other one. And so there's differences in the Hydrolite runs because they use different phase functions, and they're more or less in the middle of the measurements. So there's kind of just as much variability here from the 3 different instruments as there are from the 2 different Hydrolite runs. And this kind of agreement is as good as you're ever going to do in our field. There's just too many things that are uncertain, whether it's how to do the scattering correction on the AC9 or what phase function to use in Hydrolite or any of 50 other things. So this is, in my opinion, very good closure between instruments and models. Yeah.
Why is the Hydrolite mostly from the blue and like 500 millimeters?
I don't know the details. I know she just said, well, she used 2 different phase functions for the Hydrolite run. And I'm assuming it was the same phase function independent of wavelength, whereas in reality, the phase function, backscatter fractions and all that do depend on wavelength. So something like that is the explanation there, but I don't know exactly what it is. Here's Maria Giorgio. I know one of you is her student here, whoever it was. Brian. She's a student of this class about, who knows, 8 years ago or 10 or whatever it was. She had this, her PhD was basically getting closure between Hydrolite and measurements in the Chesapeake Bay. So it was a whole PhD's worth of work just to get the numbers to add up. But here's LW, water leaving radiance values, that her black dots here say model, that was Hydrolite, and the open spots say data, so that was measurements. And so here's a bunch of different stations in Chesapeake Bay, and you can see she gets very good agreement between Hydrolite's LWs and her measured LWs. But it was a major undertaking to get all the instrumentation and everything to work to actually be able to do that. And this paper of hers, I strongly recommend you read that because she shows how to do everything right, on all the instrument calibrations and so on and so on. Here's more of her data here. This is LUs and EDs with the measured values and the lines. She did 2 different scattering corrections for the AC9. The open circles, she just set the value at 715 equal to 0, and then the closed circles, she didn't do that. She had another correction, And you'll notice, at least on a couple of them, she gets a better agreement when she does the more sophisticated scattering correction, not just moving the curve down to 0. And then a lot of them, there's basically no difference. But in all cases, there's pretty good agreement between LU and hydrolite, or between ED and hydrolite. So once again, very nice closure. Here's plots of LW for different phase functions being used in the hydrolite simulation. So the open diamonds here are the actual measured LW data. Then this curve here, she used the Petzold phase function. Well, this was Chesapeake Bay, it looks like it had too much backscatter because she got a bigger curve here. Then she generated, she picked the backscatter fraction to be some constant value, I don't remember, 0.015, and that gave this middle curve. Then she had an eco VSF, so she let the eco VSF give her the backscatter, the AC9 gave her the total scatter. She got a wavelength and depth dependent backscatter fraction, fed that to hydrolite. Hydrolite did its magic, and then she got the curve, the bottom curve here, which is in the closest agreement to the measurements. So that's the kind of process she would go through to try to understand things like effects of phase functions on whatever she's looking at. Okay, so another paper by Alberto Tonizzo and Mike Radomski recently, they did a massive study, I think this was funded by the PACE thing, where they really wanted to look at all the errors that come into this kind of business and see how much is due to one thing and how much is another. So they have a paper that just recently came out. They compared measured hydrolite and RRSs at 5 locations, case 1 and case 2 water. They did 3 different kinds of scattering corrections for their AC9. They had measured VSFs, and then they modeled them using hydrolite's Fournier-Ferrand thing, compared all of that stuff to see how it all added up. So here's what they have. They have some labels here. BL, for example, it says measured absorption at 715, assumed to be 100% scattering error. The proportional technique, you guys know about. They had some other technique that was based on the volume scattering function and some kind of weighting thing there. Here's the equations, but one of them, they simply set the value at 715 to 0. The other one, they do the proportional thing. The other one, they do something fancier based on the actual phase function. So here's, for example, this is the absorption coefficient, the raw measurement, the value they got from the simplest AC9 correction, the value from the proportional one, and then the one they got from their fanciest version was in between. And then there's water, and there's the scattering coefficient, or half of it, for the plot here. So you can see, in this case, how you do that scattering correction in the AC9. These two were about the same. This one is significantly different. And then they had this horrendous flow chart about how they processed all their data and iterated in on everything to try to clean it all up. And then, finally up here it says, like, load the AC9 data, you go through all of this stuff, all of this kind of crap, and then it finally says, backscatter input for hydrolite. So it's an enormous, and here's the C input for hydrolite, phase function input, backscatter phase input for hydrolite. So after doing all of this stuff up here, and all I can say is read the paper. I mean, I haven't even had to try to figure this out myself. They finally get the numbers they're going to put into hydrolite to do their closure study. But it's not just take an AC9, scatter correcting, put it in hydrolite. They really had to iterate around here to really clean everything up. Okay, so they do that, and then here's RRS measurements at 4 different stations, the best they can do, and these are the different scattering corrections here, and then the measured. So some of the stations, they get pretty good agreement between both the measured and all the scattering corrections, give you pretty close to the same thing. At other stations, their most fancy scattering technique, which is the gray here, looks like it comes the closest to the measurement. The standard scattering techniques, not so good. So same thing down here. The gray is maybe a little closer to the measured than the standard scattering techniques. But once again, these guys are as good as you can get for knowing how to go to the field and get data and really think about it. And I must have had 30 emails with them answering, here's how Hydrolite does whatever. And this is still as good as they can do. So I often get people, they'll do a plot like this and they'll say, oh man, like Hydrolite's off by 30% in the blue. What's wrong with it? And I say, what do you mean, 30%? That's good agreement. This is optical oceanography, not physics. So, stop now. Don't do any more runs, publish your paper, and move on. Okay, here's some more of their data. This is RRSs at various stations, and this is, same thing. So they've got a lot of spectra, and generally they're able to get pretty good agreement between their measurements, and then Hydrolite is in the gray thing, the measurements are black. Now and then one of them will just be off, but a lot of them are, very nicely on. So just kind of look at those figures and kind of remember that's as good as you're probably going to do. So anyway, they did a big error analysis, and they found out, like in plots like this, the average error between Hydrolite and the measurement was around 20%. And when they do their error analysis, they conclude that about half of that error comes from the remote sensing reflectance measurements. So that's radiometric calibration and so forth. And about half of the error comes from the IOP measurements. So that's things like the AC9 scattering correction, and from the fact that Hydrolite ignores polarization. So about half and half. They found that using the Fournier-Ferrand phase function determined from the backscatter fraction gave results that were off on average by 23% versus the measured phase function, which was off by 20%. So the Fournier-Ferrand thing is just almost as good as having the measured phase function, assuming you have the measured backscatter fractions and our measured backscatter and total scatter that are good values. So anyway, once again, read this paper, see how they do things right, and then model your lives after them. 20 years of experience shows that the main result for bad Hydrolite runs is bad IOPs. So you usually have some concentration for chlorophyll, minerals, whatever. You run those through a biogeo-optical model that's valid for your water. You'll get good IOPs for your water. You run them through Hydrolite and you'll get good results. If you take those concentrations and run them through some biogeo-optical model that's not valid for your water, and most likely the ones in Hydrolite are not because they're based on other data and you're working in the Damascata, then you're going to get bad IOPs. You give those to Hydrolite and you'll get bad results. That's just the way the world works. Yeah.
I have a question. Can you give us a couple of cases that come to mind of examples of biogeochemical models that were selected that did not fit? Do we have some examples of the kind of regulated things in those papers?
Well, if we go back here, so here they're not using biooptical models to like convert chlorophyll to IOPs. They're measuring the IOPs directly. Now, if we, and I don't even know if they measured the chlorophyll or not, but suppose they measured the chlorophyll and this figure, chlorophyll was 3.7. If you took that 3.7 and ran it through, let's say, the new case 1 IOP model, you'd get some curve that's probably way off here because that model is based on Morel's Case 1 water and Anique Bricot's Case 1 water, etc. So it would be a fun thing to do to see how bad it is. Now it could happen that their water body was Case 1 and looks like Morel and Bricot's Case 1, and you'll get good results. But for the other stations, they'll probably be off because they did both Case 1 and Case 2 water here. And so any one biooptical model, whichever one it is, may hit correctly now and then, but in general it's probably going to be off, and it can be off by, factors of 2 or more. Okay, and sort of the moral of their story here is they measured all of these inputs, so they really worked on cleaning up the measurements and making sure they were good, and then they finally, did get good agreement with Hydrolite. Okay, so when you do a Hydrolite run and you pick one of those biooptical models, you're getting a perfectly good solution for that model. It's just that model may or may not describe your water body, and in general it probably won't. So if you want to do a generic study that says, I wonder how remote sensing depends on scattering phase function shape, or I want to know how in water ED depends on the mineral concentration in Case 2 water. So you can do a bunch of runs, you can change what kind of mineral it is, you can change the concentration, you can change the phase function. You'll get a perfectly good study then that'll give you intuition about how, let's say, LU depends on minerals versus chlorophyll versus CDOM. So those kinds of studies are great, and there's nothing wrong with them. The problem is when you want to get closure with a particular set of data in your particular water body, those models will probably not give you good results. You really do have to measure the IOPs, and then you have the data you need that describes your water body, not some generic average water body. And you can't just use like a biooptical model based on global data and apply it to the Gulf of Maine, or if you have a biooptical model that Colin put together from the Gulf of Maine from 1,000 measurements on her mooring, it then may work great for the Gulf of Maine, and it'll be totally worthless for the Yellow Sea. And there's a reason the Gulf of Maine is not yellow and the Yellow Sea is. There's a lot of, half of the Gobi Desert is going down the Yellow River into the Yellow Sea, and that's yellow dirt. So the biooptical models, they're fine on average, they're fine for generic studies, but they should not be used to simulate specific water bodies when you're doing a closure study. They're just not likely to give you good results. So you get the idea. You guys have Hydrolite. You can play with this stuff till the end of August. And, John has carefully studied heroin addicts, and he realizes what you want to do to get people hooked is you give them the first dosage for free, and then you charge them thereafter. So you're getting your first, chance to become addicted to Hydrolite for free here, and then thereafter you'll have to send John money. So anyway, but if you're good, you go home and work, you ought to be able to finish your PhD by the end of August, do all the Hydrolite runs, and then you're good. So then you kind of think, well, I don't have all these measurements. I don't have an instrument to measure the volume scattering function like Radomski has. He has an instrument called Mascot that can do that. So you do the best you can then. So if you didn't measure the VSF, well, maybe you can get the backscatter fraction, and you get that from, say, a BB9 and an AC9, and maybe if you don't have those, you can just kind of tweak the backscatter fractions till you get a good fit and see, how well can you do. And then if you tweak that, you finally get a good fit, and the backscatter fraction is 1.3%, you say that's reasonable. If it's 7%, you say, yeah, something's wrong here. That's not a typical value. Maybe you can't get good agreement between ED and LU individually, but maybe you can with their ratio, because here you're depending on getting magnitudes correct. Here you're only getting the shape of the curve correct. So you might do better with that. You play with it. You see what you can, conclude. And you just compare as many things as you can. Measured EDs from HyperPro with the Dexcel, with Hydrolite's Sky Model EDs. See how all of these things compare. You may get an idea that, oh, this one instrument just looks bad because I had 2 or 3 other things that agreed and one that was the outlier. So you play with your data and keep in mind that not getting agreement is not failure, because that's where you're going to learn the most. You kind of never learn things from good experiences. You learn things from bad experiences. And so you basically play around with Hydrolite, have fun, and see how it all works out. And then I won't go into this, but I was on one of these horrid committees where you go to DC for weeks and you advise NASA or whoever, and this was a National Academy study on the requirements for sustained ocean color research and operations. Well, I didn't contribute much because I hate sitting on committees and they don't pay you, so that means you do as little work as possible. But anyway, I did kind of design how do we put together a perfect field experiment that would really enable us to validate everything that's going on in the whole ocean color remote sensing business. And I'll just kind of, comment that people are always saying, boy, I wish I had a really comprehensive data set. Then I could validate my model. But, oh, we didn't measure this. Well, my sort of view is a comprehensive data set would include all the information you need to do a radiative transfer calculation that would propagate light from the top of the atmosphere, through the atmosphere, into the water, and finally back through the atmosphere to your satellite. And then if you had all that atmospheric IOPs, water IOPs, etc., you could then actually predict what your satellite's going to measure just given those properties. So that's a real comprehensive data set. No data set like that's ever been collected, and I'm sure never will be, even though everybody says they want one. So, first you have to get the light through the atmosphere, so you need to validate your atmospheric correction algorithms. That means you need to know the aerosols and all of this other stuff in the atmosphere. You need to validate the biooptical inversion algorithm that would retrieve, let's say, chlorophyll from RRS. So you need to know both the RRS spectrum and the value of the chlorophyll, and then you can see, does that algorithm give me the right chlorophyll? And you need to understand how the product, like chlorophyll or CDOM absorption or whatever, how does that affect the water leaving radiance? So that means you'd have to measure the water absorbing and scattering properties and in-water radiance distributions and all of this. And all of a sudden now you have like the $10 million field experiment with 30 people, in the field for 3 months, and that's just not going to happen. So, there's funding constraints. There's not enough people, there's not enough information or instrumentation, there's not enough ship time. Data collection for its own sake is not usually viewed as fundable science. You have to have some hypothesis you want to test, and to test that hypothesis, then you need to go make this measurement. But just to say, hey guys, give me $1 million, I wanted to go to the field and measure everything, that's never going to be funded, or almost never. And of course, some of the things you'd like to know, like the volume scattering function as a function of wavelength and all that, there's really not instruments out there that can do that. And don't forget to include polarization either. So anyway, you just do the best you can with the resources you have. I'll skip the rest of the stuff here, which goes into more detail about here's what you'd like to know, here's what you can actually measure with today's instruments, here's what you can use as a proxy for the things you can't measure. And so all of that's in there. We don't need to go over it here, but kind of keep it in mind. And I sort of like to think of, let's say I'm going out on the cruise next week, and here's what I'm interested in. Sit down and simulate that process in Hydrolite. And you may be thinking, well, I just want to care about how to get the chlorophyll from the remote sensing reflectance. So you go out and you measure remote sensing reflectance, and then you measure chlorophyll, and then you can see how well you're doing. And then you get back and you realize, oh, I really wish I had measured the absorption and scattering coefficients, because that's what I need to go into Hydrolite to simulate the remote sensing reflectance, blah, blah, blah. So I often just say, do a dry run of your field experiment with Hydrolite, and then you'll realize, oh, I've got this missing piece of Hydrolite input. I need to make sure I measure that when I go to the field, so I need to borrow somebody's BB9 so I can get the backscatter fraction, so I can get a better phase function. It's that kind of thing. And if you don't think about all that before you go to the field, you don't realize you needed the backscatter coefficient until you got home and tried to make sense of your data, and then it's too late. Okay, enough said. One day I threw the dart at the world map, and it hit the Lofoten Islands up here in Norway. So here's Norway, here's the Arctic Circle, and the Lofoten Islands are Arctic Norway. So that's where the dart hit, so that means that's where we have to go kayaking that year. So a bunch of us went up there and spent about 8 or 10 days kayaking along this Lofoten Island archipelago here, which is phenomenally scenic countries, absolutely spectacular, almost unpopulated. And the reason it's unpopulated is the only way you can make a living there is cod fishing. I mean, it's Arctic. Maybe you can raise a few apples or something, but you're not going to be raising, a lot of crops. You're just going to live on cod. So the Norwegians got tired of that after 1,000 years, and all the people from up here immigrated to the U.S. in the late 1800s, and it kind of literally depopulated the area. So there are little towns here and there, but not many. And now, because of its spectacular scenery, it's becoming the place where the rich people from Oslo have their summer cabins, so they can go up and hang out for a month and kayak. But anyway, if you go there, you'll find out why it is that Norwegians and Swedes make the best rain gear, because I think we had one sunny day out of like 10. And so yeah, Helly Hansen rain gear is the very best, and these Swedish made tents, they're the very best, and so they're the experts on staying dry in rainy weather. Okay, that's it. And see, you didn't think I could do it, but I actually can end lectures early. It doesn't happen often, but at least once during the class. So come back at 1:30, I guess, and we'll do today's lab.